Hello there and welcome to Science for Sleep, a quiet place where the most puzzling questions in the universe settle gently into something you can explore without strain. I'm glad you're here tonight because we're about to drift toward one of those ideas that sits right at the edge of what we can truly know. You've probably heard about black holes, those mysterious objects that swallow light itself, but there's something even more elusive hiding at their boundaries, something called an event horizon. It sounds solid, definitive, like a real place you could point to if you were brave enough to get close. Yet some of the brightest minds in physics have wondered whether event horizons actually exist as physical things, or if they're simply elegant mathematical constructions that help us organize our thoughts about gravity gone wild. It's one of those questions that feels both impossibly distant and strangely intimate. After all, we're talking about boundaries that might not be boundaries, edges that might not be edges, and the peculiar way reality behaves when space and time stretch toward their breaking points. Before we wander deeper into this gentle mystery, I'd love to know something simple and grounding. Where are you listening from tonight? What does the quiet around you feel like right now? It's curious how we're about to explore the most extreme edges of existence, while each of us sits safely in our own small corner of space and time. If these soft explorations into the unknown feel soothing to you, or if they help ease the transition towards sleep, it would mean so much if you'd like this video or subscribe. It helps this peaceful corner of the internet reach others who might need something thoughtful and unhurried to accompany their evening wind down, but only if it feels right to you. For now, let's take our first gentle step toward understanding what might be the universe's most enigmatic boundary. Are event horizons real, or are they simply the shadows cast by mathematics when it tries to describe the indescribable? What if the most fundamental boundaries in our universe exist only in the mathematics we use to describe them? Welcome to Science for Sleep, where tonight we drift into one of physics' most puzzling questions about the very nature of reality itself. I wonder where you are right now as you listen to this, perhaps settling into bed with the day's thoughts beginning to fade. Or maybe you're taking a quiet moment during a late shift when the world feels suspended between one day and the next. There's something beautifully fitting about exploring cosmic boundaries while you're here, in your own small boundary between waking and sleeping. Tonight we're going to wander gently through a question that has captivated some of the brightest minds in science. Are event horizons real physical things that actually exist out there in space, or are they simply elegant mathematical constructions that help us organize our thoughts about gravity's most extreme behavior? This isn't the kind of question that demands we solve anything or reach any definitive conclusions. Instead, it's an invitation to drift through ideas that sit right at the edge of what we can truly know about our universe. The boundaries we'll explore tonight are called event horizons, those mysterious edges around black holes where space and time curve so dramatically that nothing, not even light itself, can escape back to tell us what lies beyond. Yet some physicists have wondered whether these boundaries might be more like the equator on Earth, useful lines we draw on maps but not actual physical barriers you could touch or point to in space. As we ease into this exploration together, I'm curious about something small and grounding about your evening. What sounds are around you right now? Is there distant traffic, the gentle hum of appliances, or perhaps the kind of deep quiet that only comes late at night? It's remarkable how we're about to discuss the most extreme edges of existence while each of us experiences our own quiet edges between day and night, between consciousness and dreams. If these gentle wanderings through the mysteries of physics bring you comfort or help ease the transition towards sleep, it would mean so much if you felt moved to like this video, or subscribe to help this peaceful corner of the internet reach others who might need something thoughtful and unhurried for their evening wind down. But only if it feels right to you. Only if it feels like a natural part of your quiet time rather than an interruption to it. Could something that sounds so definitive and concrete actually be nothing more than a mathematical mirage shimmering at the edges of our understanding? Event horizons carry such weight in their name, suggesting solid boundaries you might imagine pointing toward if you were somehow floating in space near a black hole. Fixed locations where the rules of physics shift dramatically and permanently. These cosmic thresholds feel substantial, like invisible walls marking territories between the knowable and unknowable regions of spacetime itself. Yet beneath this apparent solidity lies a puzzle that has captivated brilliant physicists for decades. What if these seemingly fundamental barriers exist only within the elegant equations we use to describe gravity's most extreme manifestations? Some of the most insightful minds in theoretical physics have begun questioning whether event horizons represent genuine physical phenomena or whether they emerge as artifacts of our mathematical tools, much like shadows cast by the frameworks we employ to understand curved spacetime. There's something deeply intimate about contemplating these cosmic boundaries while we sit in our own small corners of existence, each of us occupying a tiny fraction of space and time compared to the vast scales where black holes operate. We discuss infinities and singularities while surrounded by the familiar finitude of our evening routines, the gentle limitations of our immediate environment providing a strange comfort as we explore concepts that stretch toward limitlessness. This question touches something profound about how we understand reality itself, because it asks whether the mathematics that describes our universe simply maps onto physical truth, or whether mathematical elegance sometimes leads us astray, creating compelling illusions that feel more real than reality. The puzzle feels simultaneously impossibly distant, involving objects millions or billions of times more massive than our Sun, and oddly personal because it challenges our fundamental assumptions about existence, boundaries, and the relationship between mathematical beauty and physical truth. Tonight, we're not seeking to resolve this mystery or choose between competing interpretations because the journey through these ideas offers its own rewards. Instead, we're allowing ourselves to drift through wonder, to experience the peculiar pleasure contemplating questions that exist at the intersection of human curiosity and cosmic mystery. There's no pressure to emerge with answers, no need to pick sides in ongoing scientific debates, only an opportunity to let these profound uncertainties wash over us like gentle waves, each concept settling into our awareness without demanding immediate resolution or complete comprehension. What is it about standing at the very edge of human knowledge that feels both thrilling and deeply calming at the same time? These questions we're exploring tonight transcend mere academic curiosity or intellectual exercise because they pierce straight through to fundamental issues about what reality actually means, how existence itself operates beneath the surface of everyday experience. When physicists debate whether event horizons represent genuine physical boundaries or mathematical constructs, they're wrestling with profound mysteries that touch the core of everything we think we know about space, time, gravity, and the fabric from which our universe emerges. There's something uniquely soothing about allowing ourselves to drift through these cosmic uncertainties without feeling any pressure to arrive at definitive conclusions or choose between competing theories. Unlike so many aspects of daily life where we constantly seek resolution, answers, and clear paths forward, these deep scientific mysteries invite us into a different kind of mental space where not knowing becomes perfectly acceptable, even beautiful in its own way. The unknown here doesn't represent failure or inadequacy, but rather the magnificent scope of reality extending far beyond current human comprehension. These questions exist at the very frontiers of what minds like ours can grasp, where mathematics begins to strain against the limits of language and visualization, where our most sophisticated tools for understanding nature start revealing their own boundaries and assumptions. Mathematicals. Elegance often guides scientific discovery, leading researchers toward theories that feel aesthetically pleasing, equations that seem to capture something essential about how the cosmos operates. Yet sometimes this mathematical beauty can diverge from physical reality in subtle ways, creating situations where our most elegant descriptions might not correspond directly to what actually exists out there in space and time. Event horizons occupy precisely this ambiguous territory where mathematical necessity meets physical interpretation, where the tools we use to understand black holes might be creating theories that exist more in our equations than in the universe itself. There's profound comfort in acknowledging that we exist within these mysteries rather than above them, that even our most brilliant scientific minds must navigate uncertainty and interpretation when dealing with phenomena so extreme they push against the boundaries of current knowledge. These cosmic puzzles remind us that reality remains fundamentally mysterious despite centuries of scientific progress, that the universe continues to reveal new depths of strangeness and wonder as our understanding deepens. Tonight we have permission to let these ideas wash over us without demanding they make complete sense immediately, without requiring that we choose sides or reach firm conclusions about which interpretation feels most convincing. Instead, we can drift between partial understanding and comfortable mystery, appreciating both the remarkable achievements of human reasoning and the vast territories that remain unexplored. The edge between knowing and not knowing creates its own kind of beauty, a space where curiosity can flourish without the anxiety of needing immediate answers or perfect comprehension. Mathematical frameworks that describe event horizons carry their own aesthetic appeal. Elegant solutions to Einstein's field equations that seem to capture something profound about how gravity operates in extreme conditions. Yet the relationship between this mathematical beauty and actual physical reality remains deliciously uncertain, creating opportunities for wonder that might disappear if we possessed complete understanding. These uncertainties don't represent shortcomings in science, but rather invitations into deeper appreciation for the complexity and mystery that surrounds us. Reminders that reality extends far beyond what any single mind or generation can fully encompass. What kind of mind could solve the deepest mysteries of space-time while artillery shells exploded around trenches on World War I's Eastern Front? Carl Schwarzschild possessed exactly that extraordinary intellect, working through Einstein's freshly published field equations during brief respites from military service in 1916, somehow finding mathematical clarity amid the chaos of warfare that would consume his life before the year ended. This brilliant German physicist and astronomer had already established himself through groundbreaking work in stellar photography and optical theory when Einstein's general relativity emerged, but nothing could have prepared the scientific world for what Schwarzschild accomplished in those final months of his existence. Einstein himself had struggled with his own equations, managing only approximate solutions to describe how massive objects warp the geometry of space and time around them, believing that exact solutions might remain forever beyond human reach. Yet here was Schwarzschild, stationed thousands of miles from any proper laboratory or library, carrying out calculations by candlelight and firelight that would penetrate straight to the heart of gravitational physics. The mathematical precision he achieved seems almost supernatural in retrospect, deriving exact descriptions of how space-time curves around spherically symmetric masses with an elegance that still takes physicists' breath away today. His solutions revealed something unprecedented lurking within Einstein's equations, mathematical structures that seemed to predict the existence of regions where space and time themselves would become so severely distorted that familiar physical intuitions would cease to apply. These calculations suggested that sufficiently massive objects could create boundaries beyond which nothing, not even light itself, could return to the external universe. Cosmic thresholds that would later become known as event horizons, surrounding what we now call black holes. The tragic poetry of Schwarzschild's story deepens when we consider that he contracted autoimmune disease shortly after completing this work, dying within months of making discoveries that would revolutionize our understanding of cosmic architecture. His solutions were published posthumously, carrying mathematical insights from the battlefields of Eastern Europe into the peaceful halls of academic physics, where they would quietly wait decades for recognition of their true significance. Einstein received Schwarzschild's letter containing these exact solutions with amazement and perhaps some discomfort, realizing that his theory had predicted phenomena far stranger than he had originally imagined or intended. The mathematics seemed to describe objects so bizarre that even their creator initially doubted whether such things could actually exist in the physical universe, rather than remaining mere mathematical curiosities. These wartime calculations possessed an almost prophetic quality, revealing cosmic possibilities that wouldn't be observationally confirmed until the late 20th century, when astronomers finally detected the gravitational signatures of collapsed stellar cores dense enough to create the very boundaries Schwarzschild had mathematically anticipated. There's something profoundly moving about mathematics transcending its immediate historical context, about equations derived amid human conflict revealing timeless truths about cosmic structure that would outlast the civilizations producing them. Schwarzschild's work exemplifies how mathematical reasoning can penetrate nature's deepest secrets through pure thought, uncovering aspects of reality that remain hidden from direct observation or experimental verification for generations. His solutions suggested that the universe contained regions fundamentally different from anything in human experience, places where the familiar relationships between cause and effect, past and future, inside and outside, would break down completely. The precision and beauty of these mathematical descriptions contrasted starkly with the brutal uncertainty of military life, creating an almost surreal juxtaposition between abstract perfection and concrete mortality that would define how physicists act. Why do even the most brilliant minds sometimes reject the very possibilities their own theories suggest, as if mathematical truth feels too strange to represent physical reality? Albert Einstein's relationship with black holes reveals something profoundly human about how we process discoveries that challenge our deepest intuitions about nature, showing that intellectual courage and scientific skepticism can sometimes conflict in unexpected ways. Despite creating the theoretical framework that predicted these cosmic monsters, Einstein himself dismissed them as mathematical anomalies for decades, preferring to believe that nature would somehow prevent such extreme objects from actually forming in the real universe. This resistance wasn't born from ignorance or stubbornness, but rather from an aesthetic sense that reality should possess certain reasonable limits, that the cosmos wouldn't permit situations where physics breaks down so completely that familiar concepts lose all meaning. Einstein's discomfort with black holes exemplified a broader pattern in scientific history, where revolutionary ideas encounter resistance not just from conservative opponents, but sometimes from their own creators, who struggle to accept the full implications of their theoretical breakthroughs. The mathematics of general relativity clearly pointed toward the possibility of gravitational collapse, so complete that space-time itself would develop pathological features, regions where density became infinite and causal relationships dissolved into paradox. Yet Einstein found these mathematical predictions deeply troubling, suspecting that some undiscovered principle would intervene to prevent such catastrophic scenarios from unfolding in actual stellar evolution. His 1939 paper attempted to demonstrate that black holes remained impossible by showing that realistic matter distributions could never achieve the extreme densities required for event horizon formation. This work reflected his conviction that mathematical elegance should align with physical reasonableness, that equations describing nature shouldn't predict phenomena so bizarre they violated common sense about how objects behave in space and time. The paper argued that gravitational forces alone would never overcome the natural tendency of matter to resist compression, that stellar collapse would always halt before reaching the critical threshold, where event horizons might emerge. Einstein's reasoning seemed plausible because it addressed genuine concerns about whether mathematical solutions corresponded to physically realizable situations or merely represented abstract possibilities with no counterparts in the actual universe. However, his analysis contained subtle assumptions about how matter behaves under extreme conditions, assumptions that would later prove incorrect when physicists developed more sophisticated models of stellar collapse and nuclear physics. The difference between mathematical prediction and physical belief became starkly apparent in Einstein's struggle with his own theoretical creation, illustrating how scientific progress often requires accepting implications that feel counterintuitive or aesthetically displeasing. This tension between mathematical necessity and physical plausibility has recurred throughout the history of physics, from quantum mechanics to cosmology, wherever theories predict phenomena that challenge human intuition about reality. Einstein's initial skepticism about black holes demonstrates that even revolutionary thinkers can be conservative when confronting the most extreme implications of their work, preferring interpretations that preserve familiar notions of causality and physical law. The irony deepened when later observations confirmed that the universe does indeed contain objects matching the theoretical predictions Einstein had tried so hard to avoid, vindication arriving decades after his death through gravitational wave detections and direct imaging of event horizon shadows. His resistance to black holes reflected deeper philosophical questions about the relationship between mathematical beauty and physical truth, about whether nature respects human preferences for reasonable behavior or operates according to principles that transcend our aesthetic sensibilities. The evolution from Einstein's skepticism to modern acceptance of black holes illustrates how scientific understanding advances not just through new observations, but through gradual acceptance of theoretical possibilities that initially seemed too radical to represent actual features of our universe. How can something that appears so dramatically singular in our equations turn out to be nothing more than a mathematical mirage created by our choice of measurement tools? Arthur Eddington's profound insight in 1924 revolutionized how physicists understood the apparent breakdown occurring at what we now call event horizons, revealing that these mathematical catastrophes might say more about our coordinate systems than about the actual fabric of spacetime itself. When mathematicians work through Schwarzschild's solutions using the original coordinate framework that Karl had, Employed, something seemingly terrible happens at the subcritical radius where an event horizon should form. Certain components of the metric tensor explode toward infinity, creating what appeared to be genuine physical singularities where the laws of physics would cease to function normally. These mathematical explosions looked convincing enough that many early researchers assumed they represented real features of gravitational collapse, points where space-time itself would develop pathological properties that would make normal physical processes impossible. Eddington possessed the geometric intuition to recognize that these infinities might be artifacts of perspective rather than genuine physical phenomena, much like how latitude and longitude coordinates become ill-defined and problematic at Earth's poles, without indicating anything physically unusual about those locations themselves. Standing at the North Pole doesn't place you in a region where geography breaks down or terrestrial physics stops working properly. Instead, the coordinate system we typically use to specify positions on Earth's surface simply becomes inadequate for describing that particular location in a sensible way. The mathematical framework fails while the physical reality remains perfectly smooth and continuous, requiring only a different approach to measurement and description to restore sensible behavior to our calculations. Eddington realized that the Schwarzschild coordinate system suffered from exactly this kind of breakdown at the event horizon radius, creating apparent singularities that disappeared when physicists employed alternative coordinate frameworks better suited to describing the geometry in that region. This discovery highlighted a crucial distinction between coordinate singularities, which result from poor choices in mathematical description, and genuine physical singularities, which represent actual breakdowns in the structure of spacetime itself. The revelation that event horizons might be coordinate artifacts rather than physical boundaries opened entirely new perspectives on black hole physics, suggesting that the dramatic features appearing in Schwarzschild coordinates might be mathematical illusions rather than cosmic realities. Later mathematical developments confirmed Eddington's intuition by constructing coordinate systems that remained well-behaved as observers crossed through event horizon regions, demonstrating that spacetime could be perfectly smooth and regular at these locations despite the mathematical chaos appearing in inappropriate coordinate frameworks. These alternative descriptions revealed that falling through an event horizon might be no more physically significant than crossing the equator while traveling from one hemisphere to another, a transition that appears dramatic only when viewed through coordinate systems that artificially emphasize that particular boundary. The deeper lesson extended far beyond black hole physics to illuminate how mathematical tools can sometimes mislead us about the nature of physical reality, creating apparent features that exist more in our descriptions than in the phenomena themselves. Coordinate systems represent powerful instruments for analyzing complex geometries, but they can also impose artificial structures that obscure rather than clarify the underlying physical principles governing natural processes. Eddington's insight demonstrated that distinguishing between mathematical convenience and physical truth requires careful attention to how our theoretical frameworks might be shaping our interpretations of what equations actually mean. This recognition has continued to influence modern physics, reminding researchers to remain cautious about drawing ontological conclusions from mathematical formalism, without thoroughly investigating whether apparent features might be artifacts of particular analytical approaches rather than genuine properties of the systems under study. How does scientific thinking evolve from viewing bizarre mathematical predictions as mere curiosities to accepting them as inevitable features of our universe? The transformation of black holes from abstract theoretical constructions into recognized as astrophysical realities unfolded gradually across several decades, illustrating how revolutionary ideas require time to mature within the scientific community before gaining widespread acceptance. During the 1960s, theoretical physicists began developing increasingly sophisticated models of stellar evolution and gravitational collapse, revealing that extreme objects weren't exceptional anomalies, but rather generic outcomes when massive stars exhausted their nuclear fuel and could no longer resist their own gravitational attraction. This work demonstrated that the universe should naturally produce conditions severe enough to create the very phenomena that earlier generations had dismissed as mathematically interesting, but physically implausible. David Finkelstein made a crucial conceptual breakthrough in 1958 by reinterpreting the Schwarzschild solution in terms of one-way membranes, through which matter and energy could pass inward but never return, introducing the modern understanding of event horizons as genuine physical boundaries rather than mere coordinate artifacts. His analysis showed that these regions represented fundamentally different kinds of spacetime geometry, where the usual relationships between past and future cause and effect would become dramatically altered without necessarily creating the mathematical pathologies that had troubled earlier researchers. Finkelstein's interpretation provided the first clear picture of what would later be called black holes, cosmic objects whose gravitational fields had become so intense that they created permanent isolation from the rest of the universe. The discovery of neutron stars in 1967 proved pivotal for changing attitudes toward extreme astrophysical objects, because it demonstrated that nature could indeed produce matter densities and gravitational fields far beyond anything previously observed, validating theoretical predictions about how stellar collapse could create exotic forms of cosmic architecture. These observations showed that the universe routinely generated conditions approaching those required for event horizon formation, making it increasingly difficult to argue that such extreme scenarios represented purely mathematical abstractions with no physical counterparts. Radio astronomers had detected rapidly pulsing signals from collapsed stellar cores so dense that teaspoons of their material would weigh billions of tons, confirming that gravitational compression could reach levels that pushed matter into previously unimaginable states. The existence of these neutron stars suggested that even more extreme outcomes might be possible when gravitational forces overwhelmed every known form of resistance, including the degeneracy pressure that prevented neutron stars from collapsing further. Theoretical work during this period revealed that black hole formation represented the inevitable endpoint for sufficiently massive stars, not an exotic possibility, but rather the natural consequence of physical processes operating under extreme conditions. Researchers gradually recognized that their equations were describing genuine features of cosmic evolution rather than mathematical artifacts without physical significance, leading to fundamental shifts in how the scientific community approached these theoretical predictions. The slow acceptance reflected deeper changes in physicists' willingness to take seriously the implications of their mathematical frameworks, even when those implications challenged intuitive notions about what kinds of objects could exist in the real universe. This evolution from skepticism to acceptance illustrates how scientific consensus develops through accumulated evidence and theoretical refinement rather than sudden revelations, requiring multiple generations of researchers to fully appreciate the significance of particular mathematical structures. The journey from viewing black holes as mathematical curiosities to recognizing them as inevitable astrophysical outcomes demonstrates how theoretical physics advances through gradual acceptance of increasingly radical possibilities, each generation pushing further into realms that previous thinkers had considered too extreme for serious consideration. What happens when the tools we use to navigate reality become so familiar that we forget they're just tools, mistaking our maps for the territories they're meant to describe? Coordinate systems represent one of humanity's most powerful intellectual inventions, allowing us to assign precise numerical labels to every point in space and time, transforming the continuous fabric of existence into something we can measure, calculate, and communicate about with mathematical precision. These frameworks function much like the addressing systems we use in everyday life, where street numbers and postal codes provide convenient ways to specify locations without being confused with the actual buildings, parks, and neighborhoods they help us locate. When you tell someone your home address, neither of you imagines that the numbers and letters somehow constitute your physical dwelling. Instead, everyone understands that these labels represent a standardized method for identifying where your house sits within the larger geographical landscape. Coordinate systems in physics operate according to similar principles, providing mathematical scaffolding that allows scientists to describe the positions and motions of objects through space and time without the coordinate labels themselves possessing any fundamental physical significance. The distinction between mathematical convenience and physical meaning becomes crucial when we encounter situations where our chosen coordinate framework breaks down or behaves strangely, because such breakdowns might indicate either genuine physical phenomena or simply limitations in our descriptive apparatus. Different coordinate systems can describe identical physical situations while producing dramatically different mathematical expressions, much like how the same location on Earth's surface can be specified using latitude and longitude, GPS coordinates, local street addresses, or distance measurements from familiar landmarks. Each approach offers particular advantages depending on the context and purpose of the description, but none should be considered more real or fundamental than the others, since they're all referring to the same underlying physical location. Physicists have developed remarkable skill in choosing coordinate systems that make specific calculations easier or reveal hidden symmetries in natural phenomena, but this mathematical artistry can sometimes obscure the distinction between analytical convenience and objective reality. The challenge lies in recognizing when apparent features in our equations reflect genuine properties of the physical systems we're studying versus artifacts introduced by our particular choice of mathematical language. Spherical coordinates naturally capture the symmetries of planetary orbits, while Cartesian coordinates simplify calculations involving straight-line motion. Yet both systems describe the same three-dimensional space with equal validity and accuracy. The art of selecting appropriate mathematical frameworks involves understanding how different approaches highlight or conceal various aspects of the phenomena under investigation, allowing researchers to match their analytical tools to the specific questions they're trying to answer. Sometimes coordinate systems that work beautifully in most regions of spacetime encounter difficulties in particular locations, creating apparent singularities or infinities that might have nothing to do with the actual physical processes occurring at those points. These mathematical artifacts can be remarkably persistent and convincing, appearing in multiple calculations and seeming to point toward genuine features of nature until someone discovers alternative coordinate frameworks that describe the same physics without encountering any problematic behavior. The relationship between mathematical description and physical reality becomes particularly subtle when dealing with curved spacetime, where the geometry itself determines which coordinate systems remain well-behaved and which ones encounter difficulties in various regions. Understanding this relationship requires developing intuition about how mathematical tools interact with the phenomena they're meant to describe, recognizing that our equations represent models of reality rather than reality itself, powerful and useful models that nonetheless carry their own limitations and assumptions that must be carefully considered when interpreting results. What separates mathematical illusions that can disappear with clever transformations from genuine breakdowns in the fabric of reality itself? The distinction between coordinate singularities and physical singularities represents one of the most important conceptual advances in modern theoretical physics, providing crucial insight into when our equations are misleading us about nature versus when they're revealing truly fundamental features of spacetime geometry. Coordinate singularities emerge when particular mathematical frameworks encounter limitations in their ability to describe certain regions smoothly, creating apparent infinities or undefined behavior that reflects problems with our analytical approach rather than actual pathologies in the underlying physical situation. These mathematical artifacts can be eliminated through appropriate coordinate transformations, much like how switching from polar to Cartesian coordinates resolves the apparent singularity that appears at the origin when using radius and angle measurements. Physical singularities represent fundamentally different phenomena where the geometric structure of spacetime itself becomes genuinely pathological, developing infinite curvatures or densities that cannot be removed through any choice of coordinate system because they reflect actual breakdowns in the theoretical framework rather than mere analytical convenience. Event horizons around black holes exemplify coordinate singularities because they appear problematic only when described using Schwarzschild coordinates, which become ill-behaved at the critical radius where light can no longer escape to distant observers. Alternative coordinate systems like Kruskal-Szekeres or Eddington-Finkelstein coordinates describe the same spacetime geometry without encountering any mathematical difficulties at the event horizon location, demonstrating that the apparent singularity was an artifact of the original analytical approach rather than a genuine feature of the gravitational field. Observers falling through event horizons would experience perfectly smooth spacetime geometry according to these alternative descriptions, encountering no physical barriers or discontinuities that would signal their passage across this supposedly special boundary. The situation at black hole centers presents a starkly different scenario, where all coordinate systems encounter genuine mathematical pathologies that cannot be eliminated through any known transformation technique, suggesting that physical singularities represent actual breakdowns in our understanding of how matter and energy behave under extreme gravitational conditions. These central singularities persist regardless of analytical approach, indicating that general relativity itself reaches its limits of applicability when describing regions where density and curvature become infinite according to classical theory. The persistence of these mathematical infinities across all possible coordinate choices suggests that they point toward fundamental gaps in our theoretical understanding rather than mere analytical artifacts. highlighting the need for new physics beyond classical general relativity to describe these extreme regimes. Quantum mechanical effects might prevent the formation of true physical singularities by introducing new forces or modifying gravitational behavior at microscopic scales. But such possibilities remain highly speculative, without a complete theory of quantum gravity to guide theoretical predictions. Distinguishing between these two types of singularities has profound implications for interpreting what our mathematical frameworks tell us about the nature of reality itself, helping scientists separate genuine physical predictions from analytical artifacts that might mislead theoretical understanding. The ability to transform away coordinate singularities provides powerful evidence that event horizons represent observer-dependent features rather than fundamental physical boundaries, while the persistence of central singularities suggests that our current theories encounter genuine limitations when pushed to their most extreme applications. This distinction influences how physicists approach major theoretical questions about black hole formation, information preservation, and the relationship between quantum mechanics and gravitational physics. Understanding which features of our equations reflect coordinate choices versus physical reality helps guide research toward productive directions while avoiding misleading paths that might arise from taking mathematical artifacts too seriously as indicators of fundamental physical phenomena. How can something that appears catastrophically singular in one mathematical language become perfectly smooth and well-behaved when expressed through different analytical tools? The development of alternative coordinate systems for describing black hole geometry represents one of the most elegant demonstrations of how mathematical transformations can reveal hidden truths about physical reality, showing that apparent pathologies in our equations might conceal underlying smoothness that becomes visible only when we choose more appropriate descriptive frameworks. Eddington-Finkelstein coordinates emerged from attempts to understand what happens to light rays approaching the critical radius where Schwarzschild coordinates encounter their infamous breakdown, leading to a coordinate system that follows the natural flow of photons and massive particles through the gravitational field without encountering any mathematical difficulties at the event horizon location. These coordinates demonstrate that spacetime geometry remains perfectly regular as matter and energy cross through the boundary region, revealing that the apparent singularity in Schwarzschild coordinates was purely an artifact of that particular analytical approach, rather than a genuine feature of the underlying physics. Kruskal-Szekeres coordinates provide an even more comprehensive picture by extending the mathematical description to cover regions both inside and outside the event horizon, showing that spacetime continues smoothly across this boundary while maintaining all the physical relationships predicted by general relativity. This coordinate system reveals the full geometric structure of black hole spacetime, including regions that remain forever hidden from external observers, but which nonetheless possess well-defined mathematical properties according to Einstein's theory. The transformation techniques that generate these alternative coordinate systems follow rigorous mathematical procedures that preserve all physically meaningful quantities while changing only the labels we assign to different points in spacetime, ensuring that genuine physical predictions remain unchanged even as coordinate artifacts disappear. These transformations work by choosing new time and space coordinates that align more naturally with the causal structure of curved spacetime, avoiding the artificial boundaries that arise when coordinate systems conflict with the geometric properties they're attempting to describe. The success of these mathematical transformations in eliminating event horizon singularities provides compelling evidence that such boundaries represent coordinate-dependent features rather than fundamental physical discontinuities in the fabric of spacetime itself. Physical singularities at black hole centers persist across all known coordinate transformations, demonstrating that some features of our equations point toward genuine breakdowns in theoretical understanding, rather than mere analytical artifacts that can be transformed away through clever mathematical techniques. This persistence distinguishes authentic physical phenomena from coordinate-dependent illusions, helping physicists identify which aspects of their mathematical frameworks reflect genuine properties of nature versus limitations, imposed by particular analytical approaches. The contrast between transformable and non-transformable singularities illuminates fundamental questions about the relationship between mathematical description and physical reality, suggesting that spacetime itself might possess intrinsic geometric properties that exist independently of our chosen methods for analyzing and describing them. These coordinate transformations reveal that event horizons represent surfaces in spacetime where the relationship between different observers becomes dramatically modified, creating boundaries that appear significant from some perspectives while remaining invisible to others. The mathematical smoothness revealed by appropriate coordinate systems suggests that falling through an event horizon involves no local physical discontinuity, supporting interpretations where these boundaries represent global rather than local features of black hole geometry. Understanding how coordinate transformations can reveal or conceal different aspects of spacetime. Structure has become essential for modern theoretical physics, influencing research directions in quantum gravity, cosmology, and fundamental physics, where similar issues about mathematical representation versus physical reality continue to arise. The elegant mathematical machinery developed for analyzing black hole coordinates has found applications throughout physics, wherever researchers encounter apparent singularities that might represent either genuine physical phenomena or artifacts of inappropriate analytical frameworks requiring more sophisticated mathematical treatment. What happens when the mathematical tools that guide our understanding of nature begin creating illusions that feel more compelling than reality itself? Throughout the history of physics, researchers have repeatedly encountered situations where coordinate choices and analytical frameworks generate apparent features that exist more in the mathematical description than in the physical phenomena being studied, creating persistent confusion between analytical convenience and objective truth. The early development of electromagnetic theory provides a striking example where the introduction of mathematical concepts like electric and magnetic field lines helped visualize complex force relationships, but occasionally led physicists to imagine these descriptive tools as actual physical entities, threading through space rather than useful abstractions for organizing experimental observations. Similarly, the mathematical formalism of quantum mechanics introduced wave functions and probability amplitudes that proved extraordinarily successful for predicting experimental outcomes, while simultaneously generating intense debates about whether these mathematical structures correspond to genuine physical properties or merely represent computational tools for organizing our knowledge about microscopic systems. Coordinate artifacts have appeared repeatedly throughout theoretical physics whenever researchers push mathematical frameworks beyond their natural domains of applicability, creating apparent paradoxes or singularities that disappear when more appropriate analytical approaches are developed. The danger of confusing mathematical description with physical reality becomes particularly acute when dealing with extreme phenomena where direct experimental verification remains impossible, leaving theoretical predictions as the primary guide for understanding what might actually exist in nature. Clever coordinate choices can dramatically alter the appearance of physical situations, hiding genuine complexity behind artificially simple mathematical expressions or revealing hidden symmetries that illuminate deeper theoretical principles. The art of selecting appropriate coordinate systems requires understanding how different analytical approaches interact with the geometric and causal structure of the phenomena under investigation, recognizing that mathematical convenience doesn't necessarily indicate physical significance. Einstein's original formulation of general relativity encountered this issue when certain coordinate systems made the theory's predictions appear to depend on the observer's choice of mathematical framework, leading to concerns about whether the theory possessed genuine physical content or merely represented an elaborate mathematical construction. The resolution came through developing the concept of coordinate independence, requiring that all physically meaningful predictions remain unchanged, regardless of the specific analytical approach used to derive them, ensuring that genuine physical properties could be distinguished from mathematical artifacts. This principle has become foundational for modern theoretical physics, providing a crucial criterion for evaluating whether apparent features in mathematical frameworks point toward real physical phenomena or represent analytical artifacts that might mislead theoretical understanding. The ongoing debate about spacetime's fundamental nature reflects deeper uncertainties about how mathematical descriptions relate to physical reality, with some physicists arguing that spacetime represents a genuine physical entity, while others view it as an emergent property of more fundamental processes that remain to be discovered. These philosophical questions become particularly pressing when dealing with event horizons, where the mathematical description seems to predict dramatic physical effects that might or might not correspond to genuine features of gravitational fields under extreme conditions. Coordinate independence provides a powerful tool for navigating these interpretational challenges by focusing attention on mathematical relationships that persist across different analytical approaches, helping researchers identify which aspects of their theoretical frameworks reflect robust physical predictions versus artifacts of particular computational methods. The development of increasingly sophisticated mathematical techniques for analysing curved spacetime has revealed numerous examples where apparent singularities or discontinuities represent coordinate-dependent illusions rather than genuine physical phenomena, highlighting the importance of developing multiple analytical approaches to complex theoretical problems. Understanding when mathematics misleads us requires maintaining careful distinctions between the tools we use to analyse nature and the physical systems these tools are meant to describe, recognizing that even our most elegant and successful theories remain models of reality rather than perfect mirrors of the underlying truth. What does it actually mean to see something that by definition prevents any light from ever reaching our telescopes or instruments? The Event Horizon, Telescope Collaboration's groundbreaking 20-ton image of the supermassive black hole in galaxy M87, represents humanity's closest approach to directly observing these cosmic enigmas. Yet the striking photograph reveals more about what we cannot see than what we can definitively observe about event horizon physics. This remarkable achievement involved coordinating radio telescopes across multiple continents to create an Earth-sized virtual instrument capable of resolving features near black hole boundaries, producing an image that shows a bright ring of glowing matter surrounding a dark central region that appears consistent with theoretical predictions about black hole shadows. However, the shadow itself represents light that has been gravitationally lensed and distorted by the extreme curvature of spacetime, rather than direct observation of an event horizon boundary, leaving crucial questions about the physical reality of these cosmic boundaries still open to interpretation and debate. The glowing accretion disk visible in the image exists entirely outside any event horizon, consisting of superheated plasma spiraling toward the black hole while emitting intense radiation across the electromagnetic spectrum. But this brilliant display tells us nothing definitive about whether genuine event horizon boundaries exist, or whether they represent coordinate artifacts in our mathematical descriptions. Gravitational wave detections by LIGO and Virgo instruments have revolutionized our understanding of black hole behavior by observing the spacetime ripples produced when two massive objects spiral together and merge, providing unprecedented insight into the dynamics of extreme gravitational fields, while simultaneously highlighting the interpretational challenges surrounding event horizon physics. These detections confirm that compact objects with masses and behaviors consistent with black hole predictions definitely exist throughout the universe, but the gravitational wave signatures emerge from the in-spiral process occurring outside any event horizon, rather than from direct observation of horizon formation or crossing events. The merger waveforms match theoretical predictions derived from general relativity with extraordinary precision, suggesting that our mathematical frameworks accurately describe the large-scale behavior of these systems, even if questions remain about the microscopic details of the event horizon physics and information processing. Indirect evidence for black hole existence has accumulated through decades of astronomical observations tracking stellar orbits around invisible massive objects, measuring X-ray emissions from accretion processes, and detecting relativistic jets ejected from regions near suspected black holes, all of which point toward the existence of compact objects that behave exactly as theoretical predictions suggest black holes should behave. Yet none of these observations directly confirm the existence of genuine event horizon boundaries, as opposed to surfaces that merely appear horizon-like from our external perspective, while potentially possessing different physical properties when analyzed through alternative theoretical frameworks. The fundamental observational challenge arises because event horizons represent one-way boundaries that prevent any information about their physical nature from reaching external observers, creating an inherent limitation on what can be learned about these regions through conventional astronomical techniques. Even hypothetical observers falling through event horizons would be unable to communicate their experiences to external scientists, making direct empirical investigation of horizon physics fundamentally impossible according to our current understanding of causal relationships in curved spacetime. This observational limitation forces scientists to rely primarily on indirect evidence and theoretical reasoning when evaluating competing interpretations of event horizon physics, creating unusual situations where mathematical consistency becomes more important than experimental verification for theory development. The remarkable agreement between gravitational wave observations and theoretical predictions provides strong support for the overall framework of general relativity, while leaving room for alternative interpretations about the detailed physical processes occurring near event horizon regions. What if the most accurate description of black holes comes from recognizing that external observers never actually witness event horizon formation, only the increasingly slow approach toward a boundary that might never be crossed? Russian physicists developed the intriguing concept of frozen stars during the early decades of relativity theory, acknowledging that gravitational time dilation effects make it impossible for distant observers to see matter actually cross through event horizon boundaries, creating situations where infalling objects appear to freeze just outside the critical radius, while growing dimmer and redder until they fade from detectability. This perspective emphasizes the observer-dependent nature of event horizon physics, recognizing that what appears to be dramatic boundary crossing from one viewpoint becomes eternal suspension from another, suggesting that the question of event horizon reality might depend fundamentally on whose observational frame we choose to privilege in our theoretical descriptions. Time dilation effects near massive objects cause clocks to run increasingly slowly, as measured by distant observers, meaning that processes occurring close to event horizon regions appear to unfold at ever-decreasing rates until they seem to halt completely at the critical boundary. From the perspective of external observers using telescopes and instruments located far from black holes, infalling matter never quite reaches event horizon boundaries, but instead appears to hover just outside of these regions, while its light becomes increasingly redshifted and dimmed until it falls below detectable thresholds. The frozen star terminology captures this observational reality more accurately than descriptions that assume matter definitively crosses event horizons, because external observers possess no empirical basis for claiming that such crossing events ever actually occur within finite observational timescales. Infalling observers would experience their own proper time normally, and might cross through event horizon regions without noticing anything particularly dramatic. But their experiences become causally disconnected from the external universe, making their perspective irrelevant for observers who remain outside these gravitational systems. This creates a profound perspective problem where different observational frames lead to incompatible descriptions of the same physical processes with no objective criterion for determining which viewpoint captures the true nature of what occurs near black hole boundaries. The impossibility of observing actual event horizon crossing from external frames means that the physical reality of these boundaries remains forever beyond empirical verification, creating interpretational freedom that allows multiple theoretical frameworks to coexist without definitive observational resolution. Some theorists argue that the external observer perspective should be privileged because it corresponds to the viewpoint accessible to actual scientific instruments and measurement procedures, while others contend that the infalling observer frame reveals more fundamental truths about spacetime geometry and gravitational physics. Quantum mechanical considerations complicate this interpretational landscape further, because Hawking radiation calculations suggest that black holes should eventually evaporate completely, potentially allowing information to escape back to external observers after extremely long timescales that vastly exceed current cosmological ages. If black holes do evaporate through quantum processes, then matter that appears frozen just outside event horizons might eventually be released back to the external universe through mechanisms that classical general relativity cannot describe, resolving the apparent information loss paradox while supporting interpretations that question the permanence of the event horizon boundaries. The frozen star perspective highlights how observational limitations shape theoretical interpretation, demonstrating that the apparent reality of physical phenomena can depend critically on the choice of observational frame and the timescales over which measurements are conducted. Modern gravitational wave astronomy has begun probing the dynamics of black hole formation and merger processes with unprecedented precision, but these observations still occur from external frames that cannot directly access the interior physics of event horizon regions. What happens to information when it falls into a black hole? And why does the answer to this question depend critically on whether event horizons represent genuine physical boundaries or mathematical artifacts? Stephen Hawking's discovery that quantum effects near black holes should produce thermal radiation fundamentally changed how physicists think about these objects, revealing that they aren't permanent features of the cosmic landscape, but rather slowly evaporating systems that will eventually disappear completely, taking with them all traces of the matter and energy they once contained. This revelation created one of the most profound puzzles in modern theoretical physics, because quantum mechanics demands that information cannot be destroyed, even under the most extreme conditions. Yet black hole evaporation appears to violate this fundamental principle by erasing all records of what originally fell into these gravitational traps. The paradox becomes particularly acute when we consider that Hawking radiation appears to be purely thermal, carrying no specific information about the particular matter that fell into the black hole. Much like steam escaping from a boiling kettle reveals nothing about the specific molecules of water that were vaporized to produce it. If event horizons represent genuine physical boundaries that permanently isolate interior regions from the external universe, then information falling past these boundaries would seem to be irretrievably lost when the black hole eventually evaporates through quantum process, creating an irreconcilable conflict between general relativity and quantum mechanics. However, if event horizons are coordinate artifacts rather than real physical barriers, then information might remain accessible to external observers through subtle correlations in the quantum structure of Hawking radiation, potentially resolving the paradox by showing that information is preserved in ways that aren't immediately obvious from classical analyses. Recent theoretical developments have suggested that information might be encoded in the entanglement structure connecting Hawking radiation particles to the black hole interior, creating quantum correlations that could in principle allow complete information retrieval if we possess sufficiently sophisticated measurement techniques and computational resources. These ideas have led to concepts like quantum error correction in black holes, where the information content of infalling matter gets distributed across the entire Hawking radiation output in ways that make it recoverable through appropriate quantum processing protocols. The nature of event horizons becomes crucial for understanding these information preservation mechanisms, because different interpretations of horizon physics lead to dramatically different predictions about how quantum information behaves under extreme gravitational conditions. Some approaches suggest that black holes possess quantum structure extending slightly beyond classical event horizon boundaries, creating microscopic regions where information can be accessed and retrieved through processes that classical general relativity cannot describe adequately. Alternative theories propose that event horizon formation never actually occurs from external perspectives, allowing information to remain perpetually accessible, even though it appears to be trapped when viewed through inappropriate coordinate frameworks. The resolution of the information paradox has become essential for developing unified theories that combine quantum mechanics with gravitational physics, because any complete theory of quantum gravity must explain how the information behaves under all possible physical conditions, including the extreme environments near black holes. Laboratory experiments with quantum simulators and analog black hole systems have begun testing some of these theoretical ideas, providing indirect insight into how information flows in systems with horizon-like boundaries, even though direct black hole experiments remain impossible. The debate over information preservation reflects deeper questions about the relationship between classical spacetime geometry and quantum mechanical principles, highlighting fundamental tensions between different theoretical frameworks that must be resolved before we can claim complete understanding of how nature operates under extreme conditions. Modern research on the information paradox has revealed unexpected connections between black hole physics, quantum computing, and the holographic principle, suggesting that the resolution might require radically new perspectives on the nature of space, time, and information itself. Why must some of the most important questions in physics remain forever beyond the reach of direct experimental investigation? And what does this tell us about the relationship between theoretical prediction and empirical verification? The fundamental challenge of studying event horizon physics stems from the causal structure of space-time itself, which prevents any information about the interior regions of black holes from reaching external observers, creating an inherent limitation that no amount of technological advancement can overcome using conventional observational methods. This situation represents something unique in the history of science, where theoretical frameworks make precise predictions about phenomena that cannot be directly tested through controlled experiments or detailed observations, forcing researchers to rely on indirect evidence and mathematical consistency as primary guides for evaluating competing theoretical interpretations. Cosmic censorship principles suggest that nature has arranged physical laws to prevent naked singularities from forming, ensuring that regions where classical physics breaks down remain hidden behind event horizons that shield external observers from experiencing the pathological effects of infinite spacetime curvature. This protective mechanism makes it impossible to study black hole singularities directly, while simultaneously raising questions about whether event horizons represent fundamental features of gravitational physics or merely reflect limitations in our current theoretical understanding of extreme space-time geometries. Laboratory analogies have emerged as creative alternatives to direct black hole experiments, with researchers using sonic black holes in flowing fluids and artificial event horizons in Bose-Einstein condensates to study analog versions of Hawking radiation and horizon physics under controlled conditions. These experimental systems exploit mathematical similarities between different physical phenomena, allowing scientists to investigate acoustic or optical analogies to gravitational processes while maintaining the ability to manipulate parameters and observe outcomes in real time. Sonic black holes occur when fluid flows exceed the speed of sound waves, creating regions from which acoustic disturbances cannot propagate upstream, mimicking some aspects of how gravitational fields trap light and matter near actual black holes. Experiments with these systems have successfully observed thermal radiation that appears consistent with theoretical predictions about Hawking radiation, providing indirect support for quantum field theory calculations in curved spacetime, while highlighting the limitations of such analogical reasoning. Bose-Einstein condensate experiments have created artificial horizons using laser pulses and atomic gases, allowing researchers to study how quantum correlations behave near boundary regions that share some mathematical properties with gravitational event horizons. However, these analog experiments cannot address fundamental questions about the physical reality of event horizons, because they operate in entirely different physical regimes governed by fluid dynamics or atomic physics rather than gravitational field equations. The gap between theoretical prediction and direct experimental verification has become particularly pronounced in modern cosmology and fundamental physics, where many of the most important theoretical developments involve phenomena occurring at energy scales or distance scales that exceed current technological capabilities by many orders of magnitude. This situation has forced physicists to develop new standards for theoretical validation that emphasize mathematical consistency, internal logical coherence, and agreement with indirect observational evidence, rather than relying solely on direct experimental reproduction of predicted effects. Quantum gravity research exemplifies this challenge because the energy scales where quantum effects become important for gravitational physics remain far beyond what any conceivable particle accelerator could achieve, leaving theoretical consistency and mathematical elegance as primary criteria for evaluating competing approaches. The cosmic microwave background and gravitational wave observations provide some constraints on theoretical models of extreme gravitational phenomena, but these observations probe only the low-energy consequences of high-energy physics rather than directly accessing the fundamental processes that occur near black hole horizons. Understanding the limitations of empirical investigation has become essential for developing realistic expectations about how theoretical physics advances in domains where direct experimental access remains impossible, requiring careful consideration of what types of evidence can legitimately support or refute particular theoretical proposals. How did a young physicist in Cambridge discover that the darkest objects in the universe actually glow with their own subtle light, fundamentally changing our understanding of both gravity and quantum mechanics? Stephen Hawking's breakthrough emerged from applying the principles of quantum field theory to the curved space-time geometry surrounding black holes, revealing that these seemingly perfect absorbers should actually emit thermal radiation through processes that classical physics could never predict or explain. This discovery arose from careful analysis of how quantum vacuum fluctuations behave near event horizon boundaries, where the extreme curvature of spacetime creates conditions that can transform virtual particle pairs into real particles escaping to infinity. The quantum vacuum represents a seething ocean of energy fluctuations where particle-antiparticle pairs constantly appear and disappear on timescales so brief that they remain undetectable under normal circumstances, but the intense gravitational fields near black holes can disrupt these delicate quantum processes in remarkable ways. When virtual pairs emerge near event horizon regions, the gravitational field can separate them before they have opportunity to recombine and return to the vacuum state, allowing one member of each pair to escape while the other falls beyond the point of no return. The escaping particles carry positive energy away from the black hole, while their partners contribute negative energy to the interior, effectively reducing the total mass energy of the gravitational system through this quantum mechanical process. Hawking's calculations revealed that this particle production creates a thermal spectrum of radiation with temperature inversely proportional to the black hole's mass, meaning that more massive objects emit cooler radiation while smaller black holes radiate more intensely. This inverse relationship leads to a fascinating consequence where black holes actually become hotter as they lose mass through evaporation, creating a runaway process that accelerates as the objects shrink toward their eventual complete disappearance. Quantum field theory in curved spacetime provides the mathematical framework for understanding these processes, combining Einstein's geometric description of gravity with quantum mechanical principles to predict phenomena that neither theory could anticipate independently. The discovery revealed that event horizons possess fuzzy quantum structure rather than the sharp classical boundaries suggested by purely geometric analyses, with quantum effects creating probability distributions that extend slightly beyond the classical horizon location. This quantum fuzziness introduces fundamental uncertainty into the concept of event horizon boundaries, suggesting that these regions might be better understood as transition zones, where classical and quantum physics blend together, rather than precise mathematical surfaces dividing space into distinct regions. The temperature-mass relationship discovered by Hawking implies that stellar mass black holes emit radiation so cold it would be completely undetectable against the cosmic microwave background, while hypothetical microscopic black holes would radiate intensely enough to evaporate in fractions of seconds. These predictions highlight the extraordinary range of phenomena encompassed by black hole physics, from objects billions of times more massive than our Sun that barely radiate at all to hypothetical quantum-scale holes that would explode with the energy of hydrogen bombs. The integration of quantum mechanics with general relativity through Hawking's work opened entirely new research directions in theoretical physics, leading to insights about black hole thermodynamics, information theory, and the fundamental nature of spacetime itself. His discovery that black holes possess definite temperatures and entropy values established deep connections between gravity, thermodynamics, and quantum mechanics that continue to influence modern research in quantum gravity and cosmology. The realization that quantum effects make event horizons fuzzy rather than sharp has profound implications for understanding what happens to information falling into black holes and whether these boundaries represent fundamental features of spacetime or emergent phenomena arising from more basic quantum processes. Modern developments in quantum field theory have confirmed and extended Hawking's original insights while revealing additional subtleties in how quantum effects modify classical black hole physics, demonstrating that his revolutionary discovery opened pathways toward understanding some of the deepest mysteries in contemporary theoretical physics. What happens to the quantum mechanical vacuum when it encounters the extreme gravitational fields near black holes? And why do accelerated observers experience different physical realities than their stationary counterparts? The quantum vacuum represents far more than empty space, containing a rich structure of fluctuating fields where virtual particles constantly emerge from nothingness and annihilate back into the void on timescales determined by Heisenberg's uncertainty principle, creating an invisible sea of activity that underpins all quantum phenomena. Near event horizons, these vacuum fluctuations encounter spacetime curvatures so extreme that the usual relationships between virtual and real particles begin breaking down, allowing quantum field theory to predict genuinely new physics that classical general relativity cannot anticipate or describe. The Unruh effect demonstrates that acceleration itself can cause observers to detect thermal radiation in regions that appear completely empty to non-accelerated observers, revealing that the concept of particles depends fundamentally on the observer's state of motion, rather than representing objective features of quantum fields. This remarkable phenomenon shows that an observer undergoing constant acceleration through empty space will measure a temperature proportional to their acceleration, detecting real photons and other particles where stationary observers find only vacuum fluctuations. The mathematical relationship between acceleration and perceived temperature provides crucial insight into why freely falling observers near event horizons might experience different thermal environments than those who remain stationary relative to distant reference frames. Curved spacetime modifies quantum field behavior in profound ways that go beyond simple geometric effects, creating situations where the distinction between virtual and real particles becomes ambiguous and observer-dependent in ways that classical physics never anticipated. The intense gravitational gradients near black holes create conditions analogous to extreme acceleration, suggesting that event horizon regions should appear thermally active to external observers, even though infalling observers might experience the smooth vacuum conditions according to their own measurements. Particle creation from curved spacetime represents a genuine physical process where gravitational fields provide the energy necessary to promote virtual fluctuations into real particles that can be detected and measured by appropriate instruments. This mechanism operates independently of any material sources, demonstrating that spacetime geometry alone can serve as a source of particles and energy under sufficiently extreme conditions. The mathematical formalism of quantum field theory and curved backgrounds reveals that horizons act like thermal reservoirs, with definite temperatures determined by their surface gravity, establishing deep connections between gravitational physics and thermodynamics that continue to influence modern research. These quantum effects transform the classical picture of event horizons as perfect one-way membranes into something more subtle and dynamic, where quantum correlations extend across horizon boundaries and create thermal atmospheres surrounding black holes. The emergence of thermodynamic properties from pure quantum field theory calculations represents one of the most remarkable achievements in modern theoretical physics, showing how macroscopic concepts like temperature and entropy can arise from microscopic quantum processes. Surface gravity calculations reveal that event horizon temperature depends inversely on black hole mass, creating counterintuitive situations where larger objects appear cooler, while smaller ones radiate more intensely. The quantum modifications to classical horizon physics suggest that these boundaries might possess internal structure and dynamics that remain invisible to purely geometric analyses based on Einstein's field equations alone. Vacuum polarization affects near horizons create subtle but measurable changes in the properties of electromagnetic and other quantum fields, providing potential observational signatures that could distinguish between different theoretical models of black hole physics. The interplay between quantum mechanics and curved spacetime continues to reveal new phenomena that challenge traditional notions about the relationship between matter, energy, and gravitational fields in extreme environments. These discoveries have profound implications for understanding how information, energy, and quantum correlations behave near black holes, influencing ongoing debates about information preservation and the fundamental nature of spacetime itself. What if the attempt to preserve quantum mechanical information creates a deadly wall of energy that would incinerate anything approaching a black hole, fundamentally contradicting our classical understanding of smooth spacetime geometry? The firewall paradox emerged from efforts to resolve the black hole information puzzle, suggesting that maintaining quantum mechanical consistency might require abandoning the principle that event horizons represent smooth boundaries that can be crossed without violent physical effects. Traditional general relativity predicts that observers falling freely through event horizons should experience nothing unusual during their crossing, with tidal forces remaining manageable for sufficiently large black holes and spacetime curvature appearing smooth and continuous according to local measurements. However, detailed analysis of quantum information flow suggests that preserving the information content of Hawking radiation might require breaking the quantum entanglement between interior and exterior regions in ways that would create enormous energy densities at horizon boundaries. The firewall hypothesis proposes that these energy concentrations would manifest as literal walls of high-energy particles capable of destroying any matter attempting to cross event horizon boundaries, transforming these regions from smooth geometric features into deadly barriers that would violate classical expectations about gravitational physics. This interpretation creates a dramatic conflict between two fundamental principles of modern physics: the equivalence principle demanding that freely falling observers experience no local effects from gravity, and quantum mechanical unitarity requiring that information never be permanently destroyed through any physical process. Black hole complementarity offers an alternative resolution by suggesting that different observers can have completely different but equally valid descriptions of the same physical events, with external observers seeing information preserved in Hawking radiation, while infalling observers experience smooth horizon crossing without encountering any firewall effects. This principle borrows concepts from quantum mechanics where complementary descriptions can coexist without logical contradiction, applying similar reasoning to black hole physics, where observational limitations prevent direct comparison between different observer perspectives. Entanglement structures between Hawking radiation particles and black hole interiors might hold the key to understanding how information can be preserved without creating firewalls, with recent research suggesting that quantum error correction mechanisms could maintain information accessibility while preserving smooth space-time geometry. These investigations have revealed deep connections between quantum entanglement patterns and geometric properties of spacetime, suggesting that the structure of space and time themselves might emerge from more fundamental quantum information relationships. Some theoretical approaches propose that black holes possess quantum hair, extending slightly beyond classical event horizons, creating microscopic structures that could encode information while maintaining macroscopic smoothness for infalling observers. Alternative scenarios suggest that firewalls might exist, but only under specific conditions, or for particular types of observers, creating complex landscapes where the nature of event horizon physics depends critically on detailed quantum mechanical considerations that classical general relativity cannot capture. The debate over firewalls versus smooth horizons reflects broader uncertainties about how quantum mechanics and general relativity should be unified in a complete theory of quantum gravity, with different approaches leading to dramatically different predictions about black hole physics. Laboratory experiments with analog systems have begun, testing some aspects of firewall physics using quantum simulators and optical analogies, though the connection between these simplified models and actual black hole physics remains subject to ongoing investigation. The resolution of the firewall paradox has become crucial for developing consistent theories that combine quantum mechanics with gravitational physics, because any complete framework must specify whether event horizons represent smooth boundaries or violent quantum barriers. Recent developments in holographic approaches and quantum error correction have suggested possible pathways toward resolving these contradictions, potentially allowing information preservation without requiring dramatic modifications to classical spacetime geometry. The firewall debate illustrates how attempts to reconcile different physical principles can lead to unexpected conclusions that challenge fundamental assumptions about the nature of space, time, and matter under extreme conditions. Understanding whether firewalls actually exist requires resolving deep questions about the relationship between quantum information, space-time geometry, and observational accessibility that continue to drive cutting-edge research in theoretical physics. How might our understanding of event horizons change when we finally develop theories that successfully merge quantum mechanics with general relativity? And what do these emerging frameworks suggest about the fundamental nature of space and time? Loop quantum gravity proposes that spacetime itself consists of discrete quantum building blocks at the smallest possible scales, creating a granular structure that could prevent the formation of genuine singularities by introducing quantum repulsion forces when matter becomes compressed beyond certain density thresholds. This approach suggests that classical event horizons might be replaced by quantum bounces where collapsing matter reaches maximum compression before expanding outward again, potentially eliminating the need for permanent information traps while preserving most observable features of black hole behavior. String theory offers a radically different perspective by treating fundamental particles as vibrating extended objects, rather than point-like entities, leading to calculations suggesting that black hole horizons possess internal structure related to the quantum mechanics of strings and brane as in higher dimensional spacetime. These string-theoretic models predict that event horizons might be fuzzy membranes with definite thickness, and internal dynamics rather than sharp mathematical boundaries, creating possibilities for information storage and retrieval that classical general relativity cannot accommodate. The holographic principle emerges from both string theory and other approaches to quantum gravity, proposing that all information contained within any volume of space can be encoded on the boundary surface surrounding that region, suggesting that black hole interiors might be completely described by quantum information living on event horizon surfaces. This remarkable idea implies that three-dimensional black hole physics could be entirely equivalent to two-dimensional quantum field theories existing on horizon boundaries, potentially resolving information paradoxes by showing that information never actually disappears into inaccessible interior regions. Holographic approaches have led to concrete mathematical relationships between gravitational physics and quantum field theory that allow researchers to study black hole information processing using well-understood quantum mechanical tools applied to lower dimensional systems. These techniques have revealed that quantum entanglement between different regions of space might play a fundamental role in generating gravitational attraction. suggesting that spacetime geometry itself could emerge from more basic quantum information relationships. Causal dynamical triangulation represents another approach to quantum gravity that constructs spacetime from discrete geometric building blocks arranged according to quantum mechanical principles, leading to predictions that event horizons might possess quantum fluctuating geometries that blur the distinction between interior and exterior regions. Asymptotic safety scenarios propose that gravity becomes well behaved at high energies through quantum corrections that prevent singularity formation, potentially modifying black hole physics in ways that preserve information while maintaining most classical predictions for large-scale behavior. These different quantum gravity approaches often make conflicting predictions about black hole physics, highlighting the challenges involved in developing unified frameworks that successfully combine quantum mechanics with general relativity across all energy scales and geometric configurations. Emergent gravity theories suggest that gravitational forces might arise from more fundamental quantum mechanical processes, implying that black holes and event horizons represent collective phenomena rather than basic features of spacetime geometry. The diversity of quantum gravity approaches reflects the fundamental difficulty of unifying physical theories that operate according to seemingly incompatible principles, with quantum mechanics emphasizing discrete processes and probability, while general relativity describes continuous geometric fields. Laboratory tests of quantum gravity remain extremely challenging because the relevant energy scales exceed current technological capabilities by enormous factors, forcing researchers to rely on theoretical consistency and indirect observational constraints when evaluating competing approaches. Recent developments in quantum simulation and analog gravity experiments have begun providing limited tests of specific quantum gravity predictions, though the connection between these simplified models and actual quantum gravitational physics remains uncertain. The search for a complete quantum theory of gravity has become one of the central challenges in modern physics, with potential implications extending far beyond black hole physics to include cosmology, particle physics, and our fundamental understanding of space and time themselves. What criteria should we use to determine whether something predicted by our most successful theories actually exists in the physical world? And how do we navigate situations where mathematical necessity conflicts with empirical accessibility? The question of reality in physics has evolved dramatically since the early days, when scientists could point directly to mechanical models and visualizable processes to explain natural phenomena, forcing modern researchers to grapple with increasingly abstract theoretical entities whose existence cannot be verified through straightforward observational procedures. Event horizons exemplify this challenge because they represent boundaries predicted with mathematical precision by our most successful theory of gravity, yet they remain fundamentally unobservable from external reference frames and might exist only as coordinate-dependent features rather than objective physical structures. Mathematical necessity alone cannot guarantee physical existence, as demonstrated throughout the history of science, where elegant theoretical constructions sometimes turned out to describe useful calculational tools rather than actual features of nature. The luminiferous ether once seemed mathematically essential for understanding electromagnetic wave propagation, yet subsequent experiments revealed that this supposedly fundamental medium had no physical reality beyond its role in organizing theoretical calculations before relativity theory provided more accurate descriptions. Similarly, epicycles provided mathematically precise descriptions of planetary motions, while completely misrepresenting the underlying physical processes responsible for astronomical observations, highlighting the danger of confusing analytical convenience with objective truth about natural phenomena. Unobservable entities play crucial roles throughout modern physics, from quantum mechanical wave functions that cannot be directly measured to dark matter particles that interact only gravitationally. Yet these theoretical constructs often prove essential for making sense of observable phenomena and predicting new experimental results. The challenge lies in developing principled criteria for distinguishing between unobservable entities that correspond to genuine physical features versus those that represent useful mathematical fictions without objective reference in the external world. Interpretational freedom can either accelerate scientific progress by allowing multiple theoretical approaches to compete and cross-fertilize, or it can impede advancement by permitting endless debates about untestable philosophical preferences rather than focusing attention on empirically decidable questions. The relationship between mathematics and physical reality remains one of the deepest puzzles in philosophy of science, with some researchers arguing that mathematical structures directly constitute physical reality, while others maintain that mathematics provides only approximate descriptions of fundamentally non-mathematical natural processes. Event horizon physics sits squarely within this philosophical minefield because the mathematical framework of general relativity makes precise predictions about these boundaries, while simultaneously making them empirically inaccessible in ways that prevent direct verification of their physical status. Pragmatic approaches to scientific reality focus on the predictive success and explanatory power of theoretical frameworks rather than attempting to determine the objective existence of specific theoretical entities, allowing scientists to remain agnostic about ontological questions while pursuing empirically productive research programs. This perspective suggests that event horizons should be evaluated based on their role in successful theoretical predictions about gravitational wave emissions, black hole thermodynamics, and astrophysical observations, rather than through abstract debates about their fundamental reality. Instrumentalist interpretations treat theoretical entities as useful calculational tools without requiring commitments about their objective existence, potentially resolving disputes about event horizon reality by focusing on their mathematical utility rather than their ontological status. Realist approaches insist that successful scientific theories must refer to genuine features of mind-independent reality, leading to stronger claims about the physical existence of theoretical entities like event horizons, while creating higher standards for theoretical validation. The ongoing tension between mathematical elegance and physical interpretation continues to influence how physicists approach fundamental questions about the nature of space, time, and matter, with different philosophical commitments leading to different research priorities and theoretical developments. How can equally brilliant physicists examining the same mathematical equations reach such fundamentally different conclusions about what those equations tell us about the nature of reality itself? Classical relativists maintained a strong allegiance to Einstein's original vision, where event horizons represent genuine physical boundaries marking regions from which causal influences cannot reach external observers, treating these surfaces as objective features of spacetime geometry that exist independently of coordinate choices or observational perspectives. This school emphasizes the geometric interpretation of general relativity, viewing spacetime as a fundamental physical arena where event horizons constitute real separations between causally connected and disconnected regions, much like how mountain ranges create genuine geographical barriers between different watersheds. Quantum gravity advocates challenge this classical picture by arguing that event horizons represent emergent phenomena that arise only within certain approximations to more fundamental quantum mechanical processes, suggesting that these boundaries dissolve when quantum effects are properly incorporated into gravitational physics through appropriate theoretical frameworks. These researchers propose that quantum mechanics fundamentally modifies the classical concept of sharp boundaries, replacing deterministic geometric features with probabilistic quantum states that create fuzzy transition regions rather than precise mathematical surfaces dividing spacetime into distinct domains. Mathematical purists take an even more radical position by insisting that event horizons represent nothing more than coordinate-dependent artifacts that arise from inappropriate choices of mathematical description, arguing that these apparent boundaries can always be eliminated through suitable coordinate transformations that reveal the underlying smoothness of spacetime geometry. This perspective treats event horizons as mathematical conveniences similar to the international dateline, useful for certain calculational purposes, but lacking any objective physical significance beyond their role in organizing theoretical analysis according to particular analytical preferences. Pragmatic physicists attempt to sidestep these ontological debates by focusing on the empirical utility of event horizon concepts for making testable predictions about gravitational wave emissions, black hole thermodynamics, and astrophysical observations, arguing that questions about fundamental reality matter less than the practical success of theoretical frameworks. These researchers emphasize that event horizons prove incredibly useful for organizing theoretical understanding and generating observable predictions regardless of deeper philosophical questions about their ultimate physical status or mathematical foundation. The coexistence of these competing interpretations within the scientific community demonstrates how complex theoretical frameworks can support multiple internally consistent perspectives without immediate empirical resolution, creating situations where scientific progress continues despite fundamental disagreements about interpretation. Professional physics conferences often feature heated debates between advocates of different approaches, with each school marshalling sophisticated mathematical arguments and appealing to different criteria for theoretical validity, while remaining unable to definitively refute alternative perspectives through purely logical reasoning. These interpretational differences reflect deeper tensions between different philosophical approaches to scientific theorizing, including disputes about the relationship between mathematical formalism and physical reality, the role of unobservable entities in scientific explanation, and the criteria for determining when theoretical frameworks successfully describe natural phenomena. Graduate students entering black hole physics must navigate this complex landscape of competing interpretations, often choosing mentors and research directions based partly on their philosophical inclinations about the nature of scientific knowledge and the relationship between theory and experiment. The persistence of these interpretational divisions has actually stimulated theoretical innovation by encouraging researchers to develop new mathematical techniques and explore alternative theoretical frameworks that might eventually provide empirical criteria for distinguishing between competing perspectives. Some contemporary researchers propose that these interpretational differences might be resolved through future observational advances in gravitational wave astronomy, quantum gravity experiments, or computational simulations that could provide new empirical constraints on event horizon physics. Others argue that the interpretational freedom surrounding event horizons reflects fundamental limitations in how physical theories relate to objective reality, suggesting that some theoretical questions might remain permanently underdetermined by empirical evidence. The ongoing vitality of these debates demonstrates the intellectual richness of modern theoretical physics, while highlighting the challenges involved in connecting abstract mathematical frameworks to concrete physical understanding of natural phenomena. How would our understanding of black hole formation, evolution, and ultimate fate change if event horizons turned out to be mathematical illusions rather than genuine physical barriers? The reality or unreality of event horizons carries profound implications for stellar collapse theories because it determines whether gravitational collapse creates permanent information, prisons or temporary storage systems that eventually release their contents back to the external universe through quantum mechanical processes. If event horizons represent real physical boundaries, then stellar collapse inevitably produces objects that permanently isolate interior matter from external observers, creating situations where vast amounts of cosmic information becomes irretrievably lost to the observable universe. Alternative scenarios where event horizons are coordinate artifacts suggest that collapsing matter might remain perpetually accessible to external observers through subtle quantum correlations, even though classical analyses make it appear trapped beyond the reach of conventional observation. Gravitational wave astronomy provides unprecedented opportunities to test these competing interpretations because the merger dynamics of black hole pairs depend critically on the internal structure and boundary conditions that different theoretical frameworks predict for these objects. LIGO and Virgo detections have revealed that merging black holes produce gravitational wave signatures remarkably consistent with classical general relativity predictions, yet the precision of these measurements might eventually become sensitive to quantum corrections or alternative interpretations that modify the detailed dynamics near event horizon regions. The ring-down phases of black hole mergers probe the vibrational modes of the resulting objects, providing potential signatures of whether these systems possess the internal structure predicted by quantum theories or behave like the empty vacuum regions suggested by classical analyses. Future gravitational wave detectors with enhanced sensitivity could distinguish between different theoretical models by measuring subtle deviations from classical predictions during the final moments of black hole coalescence, when quantum effects might become observable. The nature of black hole interiors represents perhaps the most dramatic difference between competing interpretations, with classical theories predicting empty spacetime regions containing only geometric curvature, while quantum approaches suggest complex internal structures capable of processing and storing information. Some quantum theories propose that black hole interiors contain highly entangled quantum states that maintain correlations with external Hawking radiation, creating possibilities for information retrieval that classical physics cannot accommodate or predict. Information preservation mechanisms vary dramatically depending on whether event horizons represent permanent barriers or temporary boundaries, with different theoretical frameworks leading to completely different predictions about the ultimate fate of matter falling into gravitational collapse regions. Holographic approaches suggest that black hole information resides entirely on boundary surfaces rather than in interior volumes, potentially eliminating the need for interior regions altogether, while preserving all observable features of these objects. Laboratory analog experiments using quantum simulators might eventually test specific predictions about information flow and quantum correlations near artificial horizon boundaries, providing indirect, direct evidence relevant to actual black hole physics. Next-generation space-based gravitational wave detectors could observe black hole mergers with sufficient precision to detect quantum gravitational effects that classical theories cannot predict, potentially resolving debates about event horizon reality through direct observational evidence. Multi-messenger astronomy combining gravitational waves with electromagnetic observations offers additional opportunities to probe black hole physics across multiple wavelengths and energy scales, searching for signatures that might distinguish between competing theoretical interpretations. The Event Horizon Telescope continues improving its resolution and sensitivity, potentially enabling direct observations of matter, dynamics near event horizon regions that could reveal whether these boundaries behave according to classical or quantum predictions. Advances in theoretical modeling and computational simulation are beginning to explore how different interpretations of event horizon physics would manifest in observable phenomena, creating testable predictions that future experiments might be able to verify or refute. The development of quantum sensors and precision measurement techniques opens new possibilities for detecting exotic physics near black holes, including subtle quantum effects that might distinguish between different theoretical approaches to understanding these extreme gravitational systems. Why do the most extreme objects in the universe often provide the clearest insights into the fundamental principles governing all of reality, and what can we learn from questions that might never have definitive answers? Event horizons serve as unique laboratories for testing the deepest foundations of physics because they represent regions where gravity, quantum mechanics, thermodynamics, and information theory converge in ways that expose hidden connections between seemingly unrelated aspects of natural phenomena. The marriage of quantum mechanics and general relativity remains one of the greatest unfinished projects in theoretical physics, with event horizon physics providing crucial testing grounds where the incompatibilities between these frameworks become most apparent and potentially resolvable. These extreme gravitational environments force physicists to confront fundamental assumptions about the nature of space, time, matter, and information that remain hidden under ordinary conditions where classical approximations work perfectly well for practical purposes. Studying black hole physics has revealed unexpected connections between seemingly disparate areas of science, including thermodynamics, information theory, condensed matter physics, and even pure mathematics, demonstrating how extreme phenomena can illuminate universal principles that operate across vastly different scales and contexts. The holographic principle emerged from black hole studies yet has found applications in nuclear physics, condensed matter systems, and quantum computing, showing how the insights gained from studying cosmic monsters can transform our understanding of the laboratory-scale phenomena. Similarly, research into black hole information paradoxes has contributed to advances in quantum error correction, entanglement theory, and quantum computation that have practical implications far beyond gravitational physics or astrophysical applications. Mathematical idealization plays essential roles throughout science by allowing researchers to isolate specific effects and develop tractable analytical models. Yet event horizon physics highlights both the power and limitations of this approach when applied to genuinely extreme physical conditions. The concept of perfectly sharp event horizon boundaries represents a classical idealization that breaks down when quantum effects are included, illustrating how mathematical precision can sometimes obscure rather than clarify the underlying physics of natural systems. Understanding the relationship between mathematical models and physical reality becomes particularly challenging when dealing with phenomena like event horizons that cannot be directly observed or experimentally manipulated using conventional scientific methods. The persistence of unresolvable questions about event horizon reality demonstrates that some of the most important scientific insights come from grappling with fundamental uncertainties, rather than from accumulating definitive answers to well-posed problems. These uncertainties drive theoretical innovation by forcing researchers to develop new mathematical tools, explore alternative conceptual frameworks, and question basic assumptions that might otherwise remain unchallenged by more conventional research programs. The debate over event horizon physics has stimulated advances in quantum field theory, differential geometry, statistical mechanics, and computational physics that have enriched our understanding of natural phenomena far beyond their original black hole contexts. Even if questions about event horizon reality never receive definitive resolution, the process of investigating these questions has already transformed multiple areas of physics, while opening entirely new research directions that continue generating valuable insights. The intellectual humility required to work with fundamentally uncertain questions about the deepest aspects of reality represents an important counterbalance to the tendency toward overconfidence that can sometimes accompany scientific success and technological advancement. Event horizon physics reminds us that the universe continues to harbour mysteries that challenge human understanding, while simultaneously revealing the remarkable power of mathematical reasoning to probe regions of reality that remain empirically inaccessible. The ongoing evolution of our understanding about these cosmic boundaries demonstrates how science advances through sustained engagement with difficult questions, rather than through simple accumulation of experimental facts or theoretical results. Future generations of physicists will likely discover new aspects of event horizon physics that current theories cannot anticipate, continuing the historical pattern where each advance in understanding reveals new depths of complexity and wonder in natural phenomena. The study of event horizons ultimately teaches us as much about the nature of scientific inquiry itself as it does about the specific physics of black holes, illustrating how the pursuit of knowledge can remain meaningful and productive even when definitive answers prove elusive. What if the solution to one of physics' most perplexing puzzles requires us to imagine that black hole interiors can somehow reach outside themselves through quantum entanglement structures that extend beyond classical event horizon boundaries? The remarkable 2019 breakthrough in black hole information and paradox research emerged from studying how quantum entanglement patterns evolve during the evaporation process, revealing that information might be recoverable from Hawking radiation through mechanisms that classical general relativity could never predict or accommodate. Researchers discovered that the entanglement entropy of Hawking radiation follows a specific pattern called the Page curve, initially increasing as radiation escapes but eventually decreasing back towards zero as the black hole approaches complete evaporation, suggesting that information begins returning to external observers during the later stages of the process. The island prescription represents a revolutionary approach to calculating entanglement entropy that includes contributions from regions that appear to lie inside event horizons, yet somehow contribute to the quantum state of external radiation through non-local quantum correlations. These calculations suggest that portions of black hole interiors, called entanglement islands, maintain quantum connections with escaping Hawking radiation despite being separated by what classical physics considers impenetrable barriers. The mathematical framework underlying island physics relies on sophisticated techniques from holographic duality and quantum field theory that allow researchers to track information flow across boundaries that classical physics treats as absolute separations between causally disconnected regions. Recent theoretical developments have shown that quantum error correction mechanisms naturally emerge in black hole systems, with the entanglement structure of Hawking radiation automatically implementing protocols that preserve and eventually recover the information content of infalling matter. These quantum error correction processes operate through redundant encoding of information across multiple radiation particles, creating resilient storage systems that can reconstruct complete quantum states even when individual particles are lost or corrupted during the evaporation process. The discovery that black holes naturally implement quantum error correction has profound implications for understanding how information can be preserved in systems where classical physics predicts irreversible information loss, suggesting that quantum mechanical principles provide fundamental protections against information destruction. Laboratory experiments with analog quantum systems have begun demonstrating similar information recovery mechanisms in simplified settings where entanglement islands can be observed and manipulated directly, providing concrete evidence that these theoretical concepts correspond to genuine physical processes. The entanglement structure connecting black hole interiors to external radiation appears to extend slightly beyond classical event horizon locations, creating quantum correlations that violate the strict causal separation predicted by purely geometric analyses of spacetime curvature. These findings suggest that event horizons might possess quantum structure that allows information to leak across boundaries that classical general relativity treats as perfect one-way membranes, fundamentally modifying our understanding of how these systems interact with their external environments. Computational studies using quantum simulators have reproduced key features of the island prescription in controlled laboratory settings, demonstrating that entanglement islands represent genuine quantum mechanical phenomena rather than mere theoretical artifacts without experimental foundations. The role of quantum error correction in black hole physics connects these extreme gravitational systems to cutting-edge research in quantum computing and information theory, revealing unexpected applications of concepts originally developed for practical quantum technologies. Modern calculations suggest that information recovery from black holes requires sophisticated quantum measurement protocols that could extract complete quantum states from carefully analyzed sequences of Hawking radiation particles, though implementing such procedures would require technological capabilities far beyond current experimental possibilities. The island framework has also provided new insights into cosmological horizons and other boundary systems in physics, suggesting that entanglement-based information recovery might represent a general feature of quantum field theory in curved spacetime rather than a special property unique to black hole systems. These developments have sparked intense research activity aimed at understanding how quantum entanglement creates effective bridges across spacetime regions that appear causally disconnected according to classical analyses, potentially revolutionizing our understanding of causality and locality in quantum gravity theories. How can researchers create miniature versions of cosmic event horizons using sound waves in laboratory fluids and ultra-cold atomic gases? And what do these tabletop experiments reveal about the deepest mysteries of black hole physics? Analog black holes represent one of the most creative experimental approaches in modern physics, exploiting mathematical similarities between different physical phenomena to study gravitational effects using systems that can be controlled and manipulated in terrestrial laboratories. Bose-Einstein condensates provide ideal environments for creating artificial event horizons, because these ultra-cold quantum gases exhibit collective behaviors that mimic certain aspects of curved spacetime geometry while remaining accessible to precise experimental measurement and control techniques. Researchers have successfully generated acoustic analogues of event horizons by creating regions in flowing condensates where the fluid velocity exceeds the speed of sound waves, preventing acoustic disturbances from propagating upstream and creating conditions mathematically similar to gravitational light trapping near black holes. These sonic horizons demonstrate horizon-like phenomena can emerge in diverse physical contexts, wherever the governing equations possess appropriate mathematical structure, suggesting that certain features of black hole physics might represent general properties of field theories rather than unique characteristics of gravitational systems. Laboratory observations of analog Hawking radiation have provided the first direct experimental evidence for thermal emission from horizon-like boundaries, confirming theoretical predictions that quantum field fluctuations near these regions should produce particle creation with specific thermal characteristics. The experimental detection of correlated particle pairs emerging from artificial horizons supports quantum field theory calculations about vacuum fluctuations while demonstrating that these effects represent genuine physical processes rather than purely theoretical constructions without empirical foundations. Acoustic black holes in flowing fluids create regions where sound waves become trapped much like photons near gravitational event horizons, allowing researchers to study how wave propagation behaves near boundaries that separate different causal regions within the experimental apparatus. These fluid analog systems have revealed unexpected connections between black hole thermodynamics and hydrodynamic turbulence, suggesting that entropy production and energy dissipation in classical fluid flows might share fundamental mathematical structures with quantum processes near gravitational horizons. Optical analogues using laser pulses in nonlinear media create artificial event horizons for electromagnetic radiation, enabling studies of how quantum field effects manifest in systems where the background medium properties can be precisely controlled and rapidly modified during experimental procedures. Laboratory investigations have confirmed that analog Hawking radiation exhibits entanglement properties consistent with theoretical predictions, providing crucial support for quantum field theory calculations about information flow and quantum correlations near horizon boundaries. However, these analog experiments operate in regimes where the underlying physics differs dramatically from actual gravitational systems, limiting the extent to which results can be directly extrapolated to genuine black hole physics without additional theoretical analysis and interpretation. The mathematical correspondence between analog systems and gravitational physics typically captures only specific aspects of black hole behavior, while neglecting other potentially important effects related to spacetime curvature, general covariance, and the nonlinear dynamics of Einstein's field equations. Despite these limitations, analog experiments have successfully tested several key predictions of quantum field theory in curved spacetime, providing valuable empirical support for theoretical frameworks that remain otherwise inaccessible to direct experimental verification using actual black holes. Recent advances in quantum simulation techniques have enabled more sophisticated analog systems that can reproduce increasingly complex aspects of black hole physics, including quantum information processing and entanglement dynamics near artificial horizon boundaries. The success of analog black hole experiments demonstrates the power of mathematical analogy in physics, while highlighting the challenges involved in connecting simplified laboratory models to the full complexity of genuine gravitational systems operating under extreme conditions. These experimental programs continue evolving toward more realistic simulations that capture additional aspects of black hole physics, potentially providing empirical guidance for theoretical research into quantum gravity and the fundamental nature of spacetime itself. What secrets about the nature of event horizons are hidden within the ripples in spacetime that we detect when black holes collide and merge across cosmic distances? LIGO and Virgo gravitational wave detectors have revolutionized our ability to study black hole physics by capturing the spacetime distortions produced during the final moments of binary coalescence, providing unprecedented direct evidence for the existence of compact objects whose properties match theoretical predictions about gravitational collapse. These remarkable instruments measure infinitesimal changes in the lengths of laser beams traveling between precisely positioned mirrors, detecting spacetime stretching and compression caused by gravitational waves propagating at light speed from cosmic collisions occurring billions of years ago. The detected waveforms exhibit three distinct phases that probe different aspects of black hole physics. In-spiral signatures reveal the orbital dynamics of compact objects approaching merger. The brief coalescence phase provides information about the actual collision process, and that ring-down signals probe the vibrational properties of the resulting black hole. Ring-down gravitational waves represent particularly valuable probes of event horizon physics because they emerge from the newly formed black hole settling into its equilibrium configuration, creating characteristic frequencies and damping times that depend sensitively on the object's mass, spin, and internal structure. These post-merger oscillations behave like acoustic vibrations in a bell, with the frequency spectrum encoding detailed information about the geometric properties and boundary conditions of the gravitational system that classical general relativity can predict with remarkable precision. Current detections show excellent agreement between observed ring-down signals and theoretical predictions based on classical black hole physics, suggesting that these objects behave very much like the vacuum solutions to Einstein's equations without requiring exotic modifications or alternative interpretations. However, future gravitational wave detectors with enhanced sensitivity might become capable of detecting subtle deviations from classical predictions that could reveal quantum corrections or alternative theoretical frameworks governing the physics of extreme gravitational collapse. Space-based missions like LISA will extend gravitational wave astronomy to longer wavelengths and higher precision measurements, potentially observing black hole mergers involving supermassive objects whose dynamics might be sensitive to quantum gravitational effects currently beyond the reach of ground-based instruments. The planned next-generation detectors could achieve sensitivity levels sufficient to probe the detailed structure of event horizons during merger processes, searching for signatures that might distinguish between different theoretical interpretations of black hole interior physics and boundary conditions. Gravitational wave astronomy also provides unique opportunities to test whether event horizons form during realistic gravitational collapse or whether alternative scenarios like frozen star formation better describe the actual dynamics of stellar core collapse under extreme conditions. The time evolution of gravitational wave signals during black hole formation could potentially reveal whether event horizons represent genuine physical boundaries or coordinate artifacts, depending on how the collapse dynamics differ between competing theoretical frameworks. Multi-messenger observations combining gravitational waves with electromagnetic signals offer additional constraints on black hole physics by correlating spacetime distortions with optical X-ray and gamma-ray emissions from matter surrounding these extreme gravitational systems. Precision measurements of gravitational wave polarization could provide new tests of general relativity in the strong field regime, while searching for exotic signatures that might indicate modifications to Einstein's theory or alternative approaches to describing gravitational collapse. The exceptional accuracy of gravitational wave timing measurements enables tests of fundamental physics principles, including Lorentz invariance, the equivalence principle, and the speed of gravitational wave propagation, providing indirect constraints on theories that modify black hole physics through quantum corrections or additional degrees of freedom. Computational advances in numerical relativity have enabled increasingly sophisticated simulations of black hole mergers that can predict gravitational wave signals with sufficient accuracy to distinguish between different theoretical models, guiding observational searches for signatures of exotic physics near event horizons. The growing catalogue of gravitational wave detections continues, expanding our empirical knowledge about black hole populations while providing increasingly stringent tests of theoretical frameworks governing extreme gravitational physics, potentially resolving long-standing debates about the nature of event horizons through precision observational astronomy. What revolutionary insights about event horizon physics might emerge when the next generation of astronomical instruments begins operating with unprecedented sensitivity and resolution during the coming decade? Enhanced event. Horizon telescope capabilities promise to transform our understanding of black hole boundaries by adding new telescopes to the global array, while incorporating advanced techniques for studying polarized light emissions from matter spiraling near these extreme gravitational systems. Polarization measurements can reveal magnetic field structures and plasma dynamics in the immediate vicinity of event horizons, providing crucial information about how matter behaves during its final approach toward regions where classical physics predicts permanent causal isolation from external observers. These polarimetric studies might detect signatures of quantum effects or alternative theoretical frameworks that modify the classical picture of smooth spacetime geometry near black hole boundaries, potentially distinguishing between competing interpretations through direct observational evidence. Future expansions of the Event Horizon Telescope will include space-based components that dramatically improve angular resolution and eliminate atmospheric distortions that currently limit ground-based observations, enabling detailed studies of smaller black holes and more precise measurements of horizon-scale physics. Multi-messenger astronomy represents a revolutionary approach that combines gravitational wave detections with electromagnetic observations across multiple wavelengths, creating comprehensive pictures of black hole systems that probe both spacetime dynamics and matter behavior during extreme gravitational events. Coordinated observations using LIGO-Virgo gravitational wave networks, alongside optical, X-ray, and radio telescopes, have already begun revealing connections between spacetime distortions and electromagnetic emissions during black hole mergers, providing new windows into the physics governing these cosmic collisions. The James Webb Space Telescope and other next-generation instruments offer unprecedented infrared capabilities for studying black hole environments, while the upcoming extremely large telescopes will achieve optical resolution sufficient to probe matter dynamics very close to event horizon scales in nearby galactic centers. Planned gamma-ray missions and neutrino detectors might reveal exotic particle emissions from black hole systems that could provide direct evidence for quantum effects, or alternative physics operating near event horizons, potentially resolving debates about the fundamental nature of these boundaries. Advanced computational techniques for analyzing multi-wavelength observational data are enabling increasingly sophisticated tests of theoretical predictions about black hole physics, comparing observed phenomena against detailed simulations based on different interpretational frameworks. The Laser Interferometer Space Antenna mission will detect gravitational waves from massive black hole mergers across cosmic history, potentially observing formation processes and dynamical evolution that ground-based detectors cannot access due to frequency limitations. Future pulsar timing arrays might achieve sensitivity levels capable of detecting gravitational wave backgrounds from countless black hole mergers throughout the universe, providing statistical constraints on black hole formation rates and evolution scenarios. Quantum sensor technologies currently under development could enable precision measurements of exotic fields or subtle spacetime distortions that might reveal quantum gravitational effects near black hole boundaries, opening entirely new experimental approaches to testing fundamental physics predictions. Next-generation neutrino observatories like IceCube Gen 2 will search for high-energy particles produced during black hole formation or evaporation processes, potentially detecting signatures of quantum effects that classical general relativity cannot predict or accommodate. The Athena X-ray mission and other planned space telescopes will study matter falling into black holes with unprecedented spectral and temporal resolution, revealing detailed dynamics that might distinguish between different theoretical interpretations of event horizon physics. Advances in artificial intelligence and machine learning are revolutionizing astronomical data analysis, enabling automated searches for subtle signatures of exotic physics in vast datasets that would be impossible to analyze using traditional techniques. The combination of improved instrumental capabilities with sophisticated theoretical modeling promises to resolve long-standing debates about event horizon reality through direct observational tests that can distinguish between competing frameworks within the next decade. These technological advances might finally provide empirical answers to questions about whether event horizons represent genuine physical boundaries or mathematical artifacts, potentially settling debates that have persisted since the early days of black hole physics through decisive observational evidence. What if the most profound questions in science are valuable precisely because they resist simple answers, and what can we learn from embracing the uncertainty that surrounds the deepest mysteries of existence? The question of whether event horizons represent genuine physical boundaries or mathematical artifacts might belong to a special category of scientific inquiries that remain perpetually open to multiple valid interpretations, each offering unique insights while none, providing complete resolution to the underlying puzzle. Throughout history, some of the most transformative scientific ideas have emerged, not from definitive answers, but from sustained engagement with questions that challenge our fundamental assumptions about how nature operates, forcing researchers to develop entirely new conceptual frameworks and mathematical tools. Uncertainty serves as a powerful engine for scientific progress by preventing premature closure around incomplete theoretical frameworks, while encouraging continued exploration of alternative possibilities that might otherwise be overlooked or dismissed too quickly. The beauty of unresolved mysteries lies partly in their ability to inspire wonder and intellectual humility, reminding us that even our most sophisticated scientific theories represent ongoing conversations with nature, rather than final statements about ultimate truth. Event horizon physics exemplifies how scientific questions can remain meaningful and productive even when they cannot be definitively resolved through conventional empirical approaches, generating valuable theoretical insights and technological innovations regardless of their ultimate ontological status. The comfort found in exploration rather than solution reflects a mature scientific perspective that values the journey of understanding over the destination of complete knowledge, recognizing that the process of investigation often proves more enriching than any particular theoretical conclusion. Different ways of being real in physics accommodate multiple levels of description and interpretation, allowing theoretical entities like event horizons to possess varying degrees of reality depending on the analytical framework and observational context being employed for their investigation. Quantum mechanics has already taught us that physical reality can be fundamentally probabilistic and observer-dependent, suggesting that questions about the reality of event horizons might not admit simple binary answers, but instead require nuanced perspectives that acknowledge multiple valid viewpoints. The mathematical structures describing event horizons possess undeniable elegance and predictive power, regardless of their ultimate physical status, demonstrating how theoretical constructs can be simultaneously useful and uncertain in ways that enrich rather than diminish their scientific value. Modern physics increasingly recognizes that the relationship between mathematical formalism and physical reality involves subtle interpretational choices that cannot be resolved through purely empirical means, requiring philosophical sophistication alongside technical expertise. Embracing uncertainty about fundamental questions like event horizon reality can actually enhance scientific creativity by encouraging researchers to explore unconventional approaches and challenge established assumptions that might otherwise constrain theoretical development. The persistence of Interpretational freedom around deep physical questions reflects the richness and complexity of natural phenomena, rather than representing failures of scientific methodology or theoretical understanding. Some questions about the nature of reality might be fundamentally undecidable within particular theoretical frameworks, while remaining scientifically meaningful and intellectually stimulating for researchers working within those contexts. The value of questions often transcends their potential answers, with inquiries into event horizon physics having already generated profound advances in quantum field theory, general relativity, information theory, and computational physics, regardless of their ultimate resolution. Scientific progress frequently occurs through gradual refinement of questions rather than sudden discovery of definitive answers, with each generation of researchers contributing new perspectives while building upon previous insights and methodological innovations. The intellectual courage required to work with genuinely uncertain questions represents an essential aspect of scientific practice that complements empirical investigation and mathematical analysis, requiring tolerance for ambiguity alongside commitment to rigorous reasoning. Event horizon mysteries remind us that science remains an open-ended enterprise, where the most important discoveries often emerge from patient engagement with questions that initially appear unanswerable, demonstrating the ongoing vitality of human curiosity in the face of cosmic complexity. What have we discovered about the nature of knowledge itself through our exploration of these enigmatic boundaries that might exist only in the mathematics we use to describe them? Our journey through event horizon physics has revealed that these cosmic boundaries serve as more than just potential features of black holes. They represent profound interfaces between the known and unknown, highlighting the fundamental limits of human understanding while simultaneously demonstrating the remarkable power of mathematical reasoning to probe regions of reality that remain empirically inaccessible. The mathematical tools we employ to analyze space-time geometry possess extraordinary ability to reveal hidden connections and predict phenomena beyond direct observation. Yet these same instruments can sometimes create apparent features that exist more within our analytical frameworks than in the physical systems we seek to understand. Event horizon investigations have illuminated how coordinate systems, theoretical assumptions, and interpretational choices can dramatically influence our conclusions about physical reality, teaching us to distinguish between genuine discoveries and artifacts of particular analytical approaches. The role of interpretation in scientific understanding has emerged as crucial for making sense of theoretical frameworks that make precise mathematical predictions while remaining open to multiple valid perspectives about their physical meaning and ontological significance. Event horizon physics demonstrates why multiple theoretical perspectives can coexist productively within the scientific community, each contributing unique insights while none claiming exclusive access to ultimate truth about these extreme gravitational phenomena. The ongoing conversation between theory and observation has proven particularly rich in black hole research, where theoretical predictions often precede observational capabilities by decades, creating dynamic relationships between mathematical insight and empirical verification that continue evolving as new technologies emerge. Our exploration has revealed that the question of event horizon reality cannot be separated from deeper issues about the relationship between mathematics and physics, the nature of scientific explanation, and the criteria we use for determining when theoretical constructs correspond to genuine features of the natural world. Mathematical beauty and physical intuition sometimes diverge in ways that force researchers to choose between aesthetic preferences and empirical constraints, with event horizon physics providing striking examples of how these tensions can drive theoretical innovation and conceptual development. The boundary between coordinate artifacts and physical phenomena has proven remarkably subtle, requiring sophisticated mathematical techniques and careful philosophical analysis to distinguish between features that reflect analytical convenience versus genuine properties of gravitational systems. We have learned that scientific understanding often advances through gradual refinement of questions, rather than sudden revelation of definitive answers, with event horizon research exemplifying how persistent engagement with fundamental uncertainties can generate valuable insights even without complete resolution. The interplay between classical and quantum perspectives on event horizon physics has revealed deep connections between apparently disparate areas of science, including thermodynamics, information theory, condensed matter physics, and quantum computation that continue inspiring new research directions. Our investigation has demonstrated that interpretational freedom can enhance rather than hinder scientific progress when it encourages exploration of alternative theoretical frameworks and prevents premature closure around incomplete understanding of complex phenomena. The relationship between mathematical formalism and physical reality remains one of the most profound puzzles in philosophy of science, with event horizon physics providing concrete examples of how this abstract issue manifests in actual research contexts. We have discovered that some of the most important scientific questions resist simple answers while simultaneously generating enormous intellectual value through sustained investigation by generations of researchers working within evolving theoretical and observational contexts. The journey through event horizon mysteries has taught us that scientific maturity sometimes involves accepting fundamental uncertainties while continuing to pursue deeper understanding through improved mathematical techniques, enhanced observational capabilities, and more sophisticated theoretical frameworks. Event horizon physics illustrates how extreme phenomena can serve as laboratories for testing the foundations of our most basic scientific concepts, revealing assumptions and limitations that remain hidden under ordinary conditions, where classical approximations provide adequate descriptions of natural processes. What draws us to contemplate boundaries we cannot cross, whether they exist at cosmic distances around black holes or within the intimate landscapes of our own understanding and experience? The human fascination with horizons extends far beyond their astronomical significance, reflecting deeper psychological patterns in how we relate to limits, boundaries, and the unknown territories that lie beyond our immediate comprehension or direct access. In everyday language, we speak of expanding horizons, broadening perspectives, and pushing beyond conventional boundaries, using spatial metaphors that connect our cosmic investigations with personal growth, intellectual development, and the universal human experience of encountering limitations. Event horizon physics resonates with fundamental aspects of human existence because it deals with questions about what lies beyond accessible experience, how we can know things we cannot directly observe, and what it means to approach boundaries that cannot be crossed or fully understood. Our daily lives are filled with horizons, both literal and metaphorical: the visual horizon that limits how far we can see across landscapes, the temporal horizons that bound our planning and memory, and the conceptual horizons that define the edges of our knowledge and imagination. Finding peace with incomplete knowledge represents a crucial skill for navigating both scientific mysteries and personal uncertainties, teaching us that meaning and value can emerge from questions themselves rather than requiring definitive resolution of every puzzle we encounter. The relationship between scientific and personal mysteries runs deeper than mere analogy, because both involve fundamental questions about the nature of reality, knowledge, and our place within larger systems that extend far beyond individual comprehension or control. Event horizon investigations mirror personal processes of approaching life's boundaries, relationships that cannot be fully penetrated, experiences that resist complete understanding, and aspects of existence that remain forever beyond direct accessibility while continuing to influence our lives. Just as external observers cannot directly witness what happens beyond event horizons, we often find ourselves unable to fully comprehend the interior experiences of other people, the ultimate meaning of our own existence, or the deeper purposes that might govern the unfolding of events around us. The metaphor of cosmic horizons illuminates how boundaries can be simultaneously limiting and liberating, creating definitions that give shape to experience while pointing toward infinite regions of possibility that extend beyond current understanding. Scientific engagement with event horizon mysteries teaches valuable lessons about how to approach personal uncertainties with curiosity rather than anxiety, exploration rather than frustration, and acceptance rather than desperate attempts to force resolution where none might be possible. The process of investigating questions about event horizon reality demonstrates how sustained inquiry can be inherently rewarding, regardless of whether it leads to definitive conclusions, showing that the journey of exploration often matters more than reaching particular theoretical destinations. Personal growth often involves learning to live comfortably with unanswered questions about identity, purpose, relationships, and meaning, while continuing to engage actively with these mysteries, rather than abandoning curiosity or settling for superficial explanations. Event horizons serve as powerful symbols for the boundaries between the known and unknowable in human experience, representing thresholds that we approach but cannot cross, while remaining sources of wonder, speculation, and creative inspiration. The contemplation of cosmic boundaries can provide perspective on personal limitations and uncertainties, helping us recognize that incomplete understanding represents a universal condition rather than individual failure or inadequacy. Scientific investigation of extreme phenomena like event horizons models approaches to mystery that emphasize patience, intellectual humility, and sustained engagement rather than demanding immediate answers or complete comprehension of complex systems. The value of questions often transcends their potential answers in both scientific and personal contexts, with some inquiries serving important roles in human experience precisely because they resist simple resolution while continuing to inspire wonder and reflection. Our fascination with event horizon physics ultimately reflects deeper aspects of human nature that seek meaning through exploration of boundaries, comfort through engagement with mystery, and connection through shared contemplation of questions that exceed individual understanding while uniting us in common wonder about the nature of existence itself. How do we return gently from the edge of cosmic mysteries to the quiet space where we began this evening, carrying with us not answers but something perhaps more valuable, a deepened sense of wonder about the boundaries that surround us? As we drift back from contemplating event horizons and the fundamental nature of reality, we find ourselves in the same peaceful place where we started, yet somehow transformed by our journey through questions that touch the very foundations of existence and knowledge. Event horizons, whether they represent genuine physical boundaries or elegant mathematical constructs, have served as invitations to wonder rather than problems demanding solution, opening doorways to deeper appreciation for the mystery and complexity that pervade both cosmic phenomena and everyday experience. The ongoing nature of scientific inquiry means that future generations will undoubtedly discover aspects of these cosmic boundaries that we cannot currently anticipate, continuing the eternal human conversation with nature while adding new chapters to our understanding of space, time, and the limits of knowledge itself. Tonight's exploration reminds us that science represents an endless journey of discovery rather than a destination to be reached, with each generation of researchers contributing new insights while inheriting profound questions from those who came before and passing even deeper mysteries to those who will follow. There's something deeply comforting about recognizing that we are part of this continuous chain of human curiosity, stretching backward through history and forward into an unknown future filled with possibilities we can barely imagine. The gratitude we feel for this opportunity to explore cosmic mysteries together reflects appreciation not just for scientific knowledge, but for the capacity of human minds to contemplate questions that extend far beyond immediate practical concerns while finding meaning and beauty in pure understanding. Event horizons have taught us that boundaries can be sources of fascination rather than frustration, thresholds that invite exploration rather than barriers that block progress, and reminders of how much remains to be discovered about the universe we inhabit. Whether these cosmic edges represent real features of spacetime or mathematical artifacts created by our theoretical framework seems less important now than the recognition that both possibilities lead to profound questions about the nature of reality, knowledge, and human understanding. The mystery surrounding event horizon physics exemplifies how science can embrace uncertainty while continuing to make progress, demonstrating that not knowing can be as valuable as knowing when it inspires continued investigation and deeper appreciation for natural complexity. As you settle into whatever quiet awaits you tonight, perhaps you might carry with you some small portion of the wonder we've shared, allowing questions about cosmic boundaries to blend gently with your own contemplation of the horizons that surround your daily experience. The beauty of boundaries lies not in their ability to separate or divide, but in their power to define spaces for meaning while pointing toward infinite regions of possibility that extend beyond current comprehension, yet remain sources of hope and curiosity. Scientific mysteries like event horizon. Physics remind us that the universe continues to harbour secrets waiting to be discovered by future generations who will approach these questions with new tools, fresh perspectives, and the same fundamental sense of wonder that has driven human inquiry since our earliest attempts to understand our place in the cosmic order. Tonight, as the gentle rhythm of your breathing carries you towards sleep, you might imagine yourself drifting peacefully through the vast spaces between questions and answers, carried by currents of curiosity that connect all human seekers across time and space in the shared adventure of trying to understand this remarkable universe we call home.